Okay, welcome back. This is part 2 of the GCSE 9-1 Physics specifications, Edexcel specifications, and we're just going to crack on with the rest of topic 2. So, next equation is going to be weight equals mass times the gravitational field strength or the acceleration due to gravity. Please note that the units can be newtons per kilogram or meters per second squared because it is also an acceleration. Okay. Mass is obviously kilograms, weight is newtons because it's a force. Right, if they ask you to describe an experiment where you have to measure a force, please make sure the tool that you use to measure that force is a Newton meter or force meter. Okay, so please use those keywords. Right. Now I'm going to look at the difference between mass and weight, okay? The rest of the world, when they say they want to lose weight, they actually mean they want to lose some of their body mass, because you can actually lose weight if you go to the moon, or you can increase your weight if you go to Jupiter, okay? Because weight is not only dependent on your physical mass, but it's also dependent on the gravitational field strength of the planet you're on, okay? Right, common practical experiment that they like to ask you about in exams is how can we accelerate this trolley? Okay, so obviously we can increase the incline, okay, so that it becomes more steeper. That will obviously increase our acceleration because the gravitational field strength, the vertical component is going to be much more stronger the more steeper the ramp is. But the other thing you can do is obviously add more masses to the hanger here, okay, so more masses here will obviously cause the trolley to fall down faster or to accelerate faster. Okay, we've talked about change in velocity and acceleration. The next thing I want to talk about is a centripetal force. Okay, so the centripetal force is always a force that acts towards the center. Okay, if the object is moving in a circular motion. So in space, in our solar system, planets that orbit our sun obviously follow circular motion, and it's primarily due to gravity, but we call it the centripetal force if it's facing the center. Similarly, with cars going around a roundabout, the centripetal force will be caused by friction, and if you've got a ball on a string and we spin it around, it's going to be caused by the tension. Okay. Right, next thing I want to talk about is inertial mass. Okay, so if you've got a sumo wrestler, okay, with a big body mass, the force that's going to be required to push him over is going to be quite large for him to change velocity, for him to accelerate. Okay, so the inertial mass is going to be the ratio of the force over the acceleration. Okay, as opposed to, let's say we've got a really tall, thin man. Okay, he's going to require a lot less force to move. Okay, so that's just gives you an idea of the force over the acceleration ratio. Okay, so please be aware of the inertial mass. It's a measure of how difficult it is to change the speed of an object. Right, Newton's third law. Okay, the way I like to think about this, I tell students if they punch the table, okay, or punch the wall, the harder you punch the wall, the more force you will feel being exerted onto your fist. So that's proof of Newton's third law. Okay, so every force has an equal and opposite reaction force. Okay, so that's Newton's third law. Next thing we're going to talk about is momentum. Momentum states that the total momentum before a collision has to equal the momentum at the end of a collision. Okay. So this is the equation for momentum. It is a vector quantity equal to mass times velocity. Units are kilograms, meters per second. Okay, so we're going to look at an example for momentum now. So let's have a look at this car here. So it's initially moving at 10 meters per second. Its mass is 1200 kilograms, crashing into this van, which has got a mass of 3200 kilograms, and its velocity is 0 meters per second. So the momentum of the car before the collision is obviously going to be its mass times its velocity, gives us 12,000 kilograms meters per second. The momentum of the van before the collision is going to be 0, because obviously 3,200 times 0 is 0, which means the total momentum before the collision is obviously going to be our 12,000 plus our 0, which is this, which means our total momentum after the collision is going to be also 12,000 kilograms meters per second. We can work out the momentum of the car after the collision because it tells us its velocity afterwards is 2 meters per second. Its mass hasn't changed, so we do our 1200 times 2, which gives us 2,400 kilograms meters per second. The momentum of the van after the collision is going to be 12,000. Remember, because our momentum after the collision has to stay the same, so we're going to minus the momentum of the car, which is 2,400, which means we're left with 9,600 kilograms meters per second. Okay, is the momentum for the van. Now, as it's asking us to work out the velocity, we then can equate our momentum is equal to our mass times our velocity. We know the mass, which is 3,200, so we're going to say our 9,600 is the momentum of the van equals our mass times our velocity. 9,600 over 3,200 gives us a velocity of 3 meters per second. Okay. So when you answer these sort of questions, please make sure you're not only writing down the maths, but you're also saying some of this. You need to state the momentum before and after the collision has got to be the same. You need to state which numbers refer to the momentum of the car and the van, or whatever the question is asking you to do, or whatever the objects are present in your question. Okay. Let's have a look at another question. So let's look at this skateboarder. So initially it says skateboarder is stationary before jumping off the skateboard, which means he's not moving, which means his momentum is obviously going to be 0 at the start. Now, the total momentum of the skateboard and the skateboarder has to be 0 as well at the end, which means we can do some nice maths. So it tells us in the question afterwards, after he jumps off his skateboard, he moves this direction at 0.4 meters per second, and it tells us his mass, 55 kilograms, which means his momentum is those two values multiplied together, 22 kilograms meters per second to the left. Okay. Now, in terms of magnitude, remember momentum is a vector, but in terms of magnitude, we know the momentum towards the right has to also be 22 kilograms meters per second. So we can equate that magnitude to the mass of the skateboard, which is 10 multiplied, sorry, no, it's asking us for the mass, because the mass is not given in this question, okay? It tells us the recoil speed of the skateboard. So we can say 22 kilograms meters per second has to equal some sort of mass times the 10, okay, the velocity. Divide 22 over 10, we get 2.2 kilograms, okay? So please bear in mind the key to answering these questions is to always state that the conservation of momentum is always going to be the case before and after a collision, okay? So the next equation is this one here, which states that force is equal to the rate of the change of momentum. So it's essentially the change in momentum over the time taken, okay? So if we look closely, if we actually increase the time taken, so if we increase the value of our denominator here, that's actually going to reduce our force. Okay, and vice versa, and the opposite is true if we decrease the time taken, that's also going to increase our force. Okay, so just simply, again, for your exams, be prepared to find the time taken, or the force, or the change in momentum. Okay. Right, the next thing we're going to look at is car safety and, airbags, seat belts, crumple zones. Why are these features important? Okay. With regards to crumple zones, essentially what you're doing, okay, you are increasing the time being exerted. So, as I said, if we increase the time taken for the momentum to change, which is the point of a crumple zone in a car, okay, you're actually going to reduce the force, okay? Same thing for an airbag. The fact that it will take time for the passenger, okay, to actually hit the front of the car or the back seat, okay, the airbag is going to increase that time interval, which means you're actually going to reduce the force that the passenger feels, okay? So that's the job of seat belts as well, okay? Right, simple experiment you can do, okay, to work out the average human reaction time, approximately about 0.2 seconds. Okay. Now, why is that important? Now, in terms of driving, you have to think about what we call the thinking distance, and this is referring to the reaction time of the driver. Okay. Now, there is an equation which states that the total stopping distance is equal to the braking distance plus the thinking distance of the driver. Okay, so now we're going to look at some factors that affect both the thinking and the braking distance. One of those are the speed, okay, at which you're going at. Simply for the simple fact that when you're moving at a fast pace, your ability to judge distances actually decreases. Okay, so it's not as if you're walking; you're actually moving at a very fast pace, and there's a reason why they ask you to maintain a good distance with respect to the car in front of you. Okay, so we're going to look at why that is in terms of the braking distance in a second, but just simply accept the fact that when you're traveling at a fast pace, your ability to judge distances actually decreases. Other things, simple distractions such as using a mobile phone, okay, listening to loud music, eating, just general tiredness or being under the influence of alcohol or drugs will definitely impair your ability to judge distances. With respect to the braking distance, that simply refers to the mechanics of the car in the road, or conditions of the road, I should say. So your brakes, quality of your brakes and tires, plus the weather conditions and the road will obviously all play into your car's ability to actually physically slow down. Okay. Now, if we look back to this equation, force equals to the change in momentum. So if we're coming to a final halt, it means that our final velocity is obviously going to be 0. So we're going to, in order to work out the force to stop a car, it's going to be literally the mass times its velocity, its initial velocity, over the time it takes. Okay, so if you look at this example here, it says cars have a mass of around 1,500 kilograms and 30 miles per hour is around 13 meters per second. It says calculate the force felt. The car goes from 30 miles per hour to stationary in 0.07 seconds and 2 seconds. So if we look at where to cause the car to stop in 0.07 seconds, okay, look at the force required. Okay, that's 278,571 newtons. That's a lot more than the force required to stop it in 2 seconds. So you can begin to see that the brakes on your car, can only do so much. And obviously, the heavier your car is, and if it's moving at a fast pace, it's going to require a large force to actually cause it to come to a standstill. Okay, so that's just a calculation there for you to be familiar with. Again, simple maths here. Okay, stopping distance is equal to thinking distance plus braking distance. Make sure you're comfortable with that. And look, 70 miles per hour. Look at the braking distance. Okay, we can see it is slowly increasing as speed increases, in addition to your thinking distance. Okay, so that's a trend you should be able to explain, and we've already talked about how speed does affect both thinking and braking distance. Right, now we're going to talk about work or work done, and the thing about work done in terms of physics, it's not literally your schoolwork, it is a type of energy. So its units is going to be in joules, and the equation is force, okay, times the distance moved in that particular direction that the force is being exerted in. Okay, so again, we're going to be practicing this equation later on, but for now, just please bear in mind work done is equal to force times distance. Another equation you should be familiar with is the kinetic energy equation. Okay, it's equal to half times mass times velocity squared. Now this is very important because when the brakes are applied to a moving vehicle, the braking force does work to stop the car. Okay, and we can use this equation here to work that out. So if we've got a total stopping distance, we know the mass of the car, we know the speed it was traveling at, we can work out the force required to actually stop the car. Okay. We can also rearrange it to work out the total braking distance, okay, where we make D the subject. Now, you should just, by looking at the kinetic energy, okay, equation, or this v squared term here, okay, how distance is affected by speed. Okay, so if speed is doubled, because it's a squared term, our distance is actually going to increase by 4 times. Okay, again, if it's tripled, it will increase by 9 times. If it's halved, it will increase by a quarter. Okay, so you know, speed definitely has a huge impact on your braking distance. So please bear that in mind. Right, finally, you should ask yourself what happens to all this kinetic energy. Well, it simply gets lost to the surroundings, okay, in the form of heat and a bit of sound, okay, through the tires interacting with the road surface. So that brings this video and the P2 topic to an end. Please make sure you go back through any sections of this video. If I went too fast, please go back and look at the questions and look at the answers that I've written down here. Okay.